only one conductor, one conductor, one conductor. So now we normally do bundling of conductor. Bundling of conductor has a lot of advantages on transmission line. Bundling means that we are adding conductors in the same phase. This is called bundling. Not like we are adding any other fourth phase. For example, I add two conductors here, two conductors here, two conductors here. So it is called the bundling conductor. Because this is the view you are watching here is the cross-sectional area of transmission line. If I will cut transmission line and see parallel, then I will see the position of conductors like this. So these three, bundling of conductor means I am adding one conductor here, one conductor here, one conductor here. I can add even two. I can add even four. Normally we go up to four. So we must know how to calculate the inductance in each bundling conductor. So first we study single conductor, then two wide conductor, then three equal spacing, then three unequal spacing transposed line, and then now we are going for bundling conductor. Bundling will reduce the inductance because effective radius increases. It will increase the value of effective radius, and you know that the value of by watching the value of effective radius, if we increase the, it is denominator, if we will increase the value of effective radius, the inductance will reduce. So bundling can reduce the overall inductance of any transmission line. But here, how we will calculate it? So here the inductance will be the same, 2 multiplied by 10 to the minus 7 natural log of mutual GMD divided by self GMD. GMD is actually geometric mean distance. Now I will tell you how you can relate this formula with the first formula we tried. This is the first formula, the basic formula. So I will just paste here and then you will see. Okay, I have to include it like this. Okay, just why this formula? This formula is the same almost in case of bundle conductor. Okay, this is, I am talking about this conductor only. Then we will calculate the inductance of this, inductance of this, inductance of this, and then we will add up these inductances. So, but sorry, this is actually the not LT. This is you can say that LA. For example, for phase A bundle connector. So
okay.
This is this formula is similar with this one, but what is changing here? In case of D, we are writing GMD, and here instead of radius, we are writing self GMD. Okay, GMD is geometric mean distance. Now, if you will see the only single conductor, then his self geometric mean distance is its radius. So actually here there are two radius, and maybe there are some distance between them, maybe 1 centimeter, 2 centimeter, 5 centimeter, that we will discuss later. So that's why we are not talking about radius now, we are talking about GMD, because you know that radius we can also say that, okay, one conductor, I will say radius R, but there are two conductors bundled together, so I cannot say that R, I will say GMD. The
Is GMD only used in the bundled?
what?
The GMD is only used in the bundled conductor?
Yes, GMD is only used in bundled conductors. So this is geometric mean distance. Okay, so I'm just placing this distance with geometric mean distance mutual. Mutual means this distance from these four conductors. This we call mutual. And about self, we call these two is called we call self. Why we call self? Because these are on single phase. You know, phase one, phase two, phase three.
In the same bundle.
Yes, we just added extra conductors. Sometimes we add this conductor to reduce the inductance of transmission line, and sometimes we add this conductor to carry more power, because more conductors mean we are transmitting more power in transmission lines. So bundling is very important, and in high transmission lines, we always do this. So we must know how to calculate the inductance of bundled conductors. So in mutual, here, so self GMD, you understood it, right? It's mutual is itself and self. Now, how we will calculate GMD, I will explain in next slide. But firstly, you understand?
I just want to understand the mutual GMD. Is it like the distance between A and B, B and C, and A and C?
Yes, mutual GMD is like, yes,
Okay.
you can say like this of same phase. You know, mutual GMDs, it means that the distance between the same phase conductors. We can we can say like this. But self GMD is calculated the distance between from here to here, here to here, here to here. I will explain it next slide.
I misunderstood it. I thought that the self GMD is between the bundles and the mutual is between
No, no, it's
each.
not. Because we are considering it as a single phase. So we just consider this as a single conductor, but it is bundled. We normally call it single conductor, but we call it bundled conductor. This is bundled conductor. Okay. So now you know that how we can relate these two formulas.
Yes.
Okay. So I will explain that how we can calculate the mutual GMD and the self GMD. I can explain these two. Okay. Let me take a break of 4 minutes. It's okay.
Yes, yes, sure. It's fine.
Because and you can also, I'm sending you PPT, and then you can also revise it for 5 minutes. And if you have any question, you can ask me in next class. We will start next class after 5 minutes. Okay.
Okay, sure. Thanks a lot.
Thank you. Thank you. after the lecture. Okay. So I was talking about the bundling of conductors, that how you'll find the inductance in bundled conductors. So after that, I compared the two equations of the basic equation we derived with this one, and instead of D, we are getting here GMD, mutual GMD, and instead of R, we are getting here self GMD. Actually, the self GMD is similar with the radius, because here we have increased the radius, so it effective resistance increased. You can see we are talking about self GMD, so that's why our all inductance of the bundled conductor transmission line decreases. That help us in power transmission and reduce losses, and help us to take extra power to the receiving end. So how we will calculate self GMD? So this is actually the problem of lecture. This is related to the problem of lecture 1, your professor you just provided me last time. So you must have to understand this. Okay, so for example, I have to firstly I'm just talking about the one phase, that in this phase I have two conductors, same radius. I have two conductors, this one and this one. The distance between these two conductors, I call it D. Okay, I'm talking about self GMD. So I will just look upon the phase on single phase. Later on, I will go about the mutual GMD. So, so we have to look upon this formula first. So after that, you will understand the concept. This formula, we try it here. R1 and R2. Okay. So if you closely look this one, that I'm calculating this, I'm including all the values of different distances in my equation. So same here, I will calculate like the self GMD. I will, okay. So first, distance of conductor 1 with itself. So what conductor 1, for example, I say that this is conductor 1 and this is conductor 2. Okay, this conductor 1 and conductor 2. So we always take the distance, self distance, plus the distance up to another conductor, like we do in radius and the D, the effective radius. So the distance of conductor with itself, the effective distance, the effective radius, we call it R slash. Okay, the radius, as the radius of both conductors is same, so I am not talking about here R1 or R2. I just say R. So the distance of conductor 1, this is conductor 1, this is conductor 2. The distance of conductor 1 with self. So this is R dash. I will take R dash. This distance of conductor 1 and 2. I explain here. This is D, the distance between two conductors. We can call it like this. The distance of conductor 2 with 1. Now here firstly I have to check the distances with respect to conductor 1, then I will check the distance with respect to conductor 2. This is very important. So with respect to distance conductor 1, I have two distances. First is its radius, and second this point, at the point where second conductor is present. So the effective radius, I will take it R slash, and the point I will take it D, which is given. After that, distance of conductor 2 with 1. Then I will move towards the conductor 2. Okay, the distance of from 2 to 1. Or you can say I have to write this first and this second actually. So firstly, I will take the distance of conductor. I should know about the distance of conductor 1 with itself, which is R slash. The distance of conductor 1 with 2, with respect to this, which is D. Then I will move towards the conductor 2, distance of conductor 2 with self, and then distance of conductor 2 with 1 or from 1. So I will take 4 distances because here there are 2 conductors. So firstly, conductor we must know, because here distances involved the inductances. So firstly, we must know the mutual inductance and self inductance. Then we go for mutual inductance. So here this distances. Firstly, I know the self distance. The self distance of conductor 1 is r slash effective radius, and the self distance of conductor 2 is also r slash. Then the distance of conductor 1 to 2 is d, and the distance from conductor 2 to 1 is d. So I have to write d 2 times, because we must know that, because same current is flowing from both conductors, and the inductance, if I want to calculate the inductance of this conductor, I should know the distance of this conductor from this conductor. So if I want to calculate the conductor inductance of this conductor, conductor 2, I should know, should include the distance of this conductor from this conductor. So in case of 2 conductors, we have 4 distances. Similar, in case of 3 conductors, we have 9 distances. I will show you how. So you got this point? You want to ask something here?
No, am I going to like add them all together, or it will have a specific rule?
Up to most together, I didn't understand. Can you repeat?
I mean, here we're calculating the self GMD. So
Yes.
we get each one with itself and then each one with the other, which is the D right
Okay,
now.
I'm explaining it. So you are confused that how we call it self GMD.
Yes, but now I understand it.
Okay, now you understood. Yes, because these 2 conductors are same phase conductors, not different phase. So that's why we call it self GMD. After that, we will also see the effect of this conductor with other 2 conductors, different phase conductors, like here. Now I am just on this point. So I have to calculate the, if I want to calculate the inductance, I know the self GMD of this phase. Then I will calculate the inductance of this phase. Then I will move towards this one. I have to know about the self uh, GMD of this one, mutual GMD and self GMD both of this one. Then I can calculate LB in case of phase B, then in case of phase C, and then I will add up all these. So this is the process. So here, uh, now how I will calculate a self GMD. So self GMD will be like r slash divided by d raised to power under 1 by 2 or under root. How it comes like this, I am explaining this. Okay, here is mistake. Actually, this is not divided by, actually this is multiplied. This is the value of self GMD. Now, how I will know the self GMD? You see here, this value will actually, how it becomes like this. I am explaining this because you must know the root, that how the value is r slash multiply by d. Why it's like that? So I'm explaining now. Now, normally, I will, if I want to calculate the GMD, what I will do, I will justly put the, firstly I will multiply all these. I will multiply all these values. R multiply just like we did in DAB, DBC, DCA last three phase conductor.
Okay.
I am going to multiply all these distances. So how to you know that R slash multiply by R slash. I can just write that from starting from here R slash multiply by D multiply by T and then multiply by R slash. So how many distances are there? 4. So I will just like before I explained, I will write 1 divided by 4. So d multiplied by d, it will become d square. R slash multiply by r slash, it will become r slash square. So I can further solve it like this, d square. Yes, I can d multiply by, okay, here I cannot write well. So this is multiply, not plus, square. Raised to the power 1 divided by 4. So 2 1 and 2 2. Therefore 2 multiplied by 2 is 4. So in the result I got r slash multiply by d raised to the power 1 divided by 2. This from here. So you must know, because these I'm explaining this, because sometimes conductor will be present like this. So sometimes there will be 3 conductors. I will explain in next step that how we will calculate the GMD of 3 conductors. So you should know that no matter how many distances, we have to include all the distances and multiply with each other. And then we will count how many distances raised to the power 1 divided by numbers. Like here are 4 distances. I have written here 4. If here are 3 distances, I should have written 3 and include all the 3 distances inside. But here the distance, number of distances 1 2 3 4, number of values, number of lengths or number of displacements are 4. So I will just multiply all these 4 and then raise the power 1 divided by 4, and then like 1 divided by 2. Then here it comes the equation r slash multiply by d raised power 1 divided by 2. You got this point?
Yes, I got it.
Okay, so now I am moving towards so this is the self GMD, because if you will see, I am opening your professor's notes, then you will understand. Okay, starting from here, he explained all these things. Like I explained that the distance between, look at here, the first slide, that is the same thing, like how we will do about 2 conductors. This is the same answer he proved here. You understood it? This is the same thing we proved in our slide. L is equal to 4 multiplied by 10 to the minus 7 natural log of d divided by r slash. Then for different conductors, she explained in different way. Actually, a difficult way. But here I am just telling you that here GMD. Okay. Look, here is you look, there are 4 distances and raise the power 1 divided by 4. This problem I will solve for you in next lecture, but I just want you to know about that it is same like your professor did. D1 D2 D3 D4 4 distances and raise the power 1 divided by 4. So look, you must know here A B C means this is A B, this is A conductor, this is B conductor, this is C conductor, this is side X. I think these are on one phase and these are on another phase. So for one phase, we have to calculate the self GMR and then mutual GMR for
Will
this.
it be like 9 distances?
Yes, like no, in this, I will explain in my next slide that how we will find the distances in case of more than two conductors. But here I'm
Okay.
saying this. Yes, you must know the distance between, for example, here it is similar, like you must know the radius and then distance from this point to this point, this point, this point. I will explain in my next slide, and then you will understand this problem a bit, but not completely,
Okay.
because after I will solve it, this problem for you, this the similar problem explained in lecture one of your professor, then I will then you will understand all the things. So here I'm talking about the, in case of three conductors. For example, we have three conductors here. So, so okay, this is not the three-phase conductor. Okay, it looks similar. Okay, don't confuse with the three-phase conductor. As I explained in last second or third slide, it's not the
Okay.
three-phase. All the three conductors are on same phase. Okay.
Okay.
Uh, you are okay. So there are, for example, this is if conductors are placed like this. So I'm explaining how the conductor is can be placed like this. Look, the conductors can be placed like this. For example, two conductors here, two here. So these conductors can also be placed like this. This first phase, for example, the second phase. These distances will be similar because I am here. You know some differences in three, all of these three.
That's like bundled 3-phase.
Yes, yes, yes. We can bundle like this too. So bundling can be different, but don't confuse it with three phase. This is one phase, this is second phase, this is third phase. So these are bundled like this. So I am talking about the this one only, this specific. Okay, I am talking about this any phase of these. Okay, so here I draw it like this. So so for example, we have conductors which are placed like this. For example, this is number one, conductor number one, conductor number two, and conductor number three. So this is the distance. Distance is the same for all of three conductors, and this will happen. Okay, I am explaining. Point number one. Firstly, we will look about conductor number. We will talk about conductor number one. So distance of conductor one with self like this r slash. Okay, let's suppose that normally is the same like problem. All the conductor will have same radius. So we are not talking about r1, r2, r3. We just say r. Distance of conductor one with itself or with self r slash. Then distance of conductor 1 with 2, which is D. I put it here. Then distance of conductor 1 with 3, which I put here. Distance of conductor 2 with self. Then I move towards the distance of conductor 2. 2 with self slash 2 with 1 D, 2 with 3 D, and distance of conductor 3 with self R, then D, then D. You understood this? You want to ask something?
Yes. This is like you're, just like you said earlier, you're zooming in to the bundle. You know, 1, 2, 3. This is
Yes.
bundle, right?
Yes.
Okay, I got it.
You got it right, because these bundles are not when you will look transmission line, for example, in your daily life when you drive outside, you will look the high towers. You are saying that you will see that all sometimes 4 conductors are punched together, 4 or 5 conductors in high transmission line like 500 kV or 700 kV. We are talking about this. You when you will go in countryside or outside of city, if there are some poles, installed poles of high voltage, more than 500 kV, you will see this bundling. That one phase have lot of conductors, not different phase. One phase have lot of conductors, then second phase have lot of conductors, then third phase. But all these numbers are same and distances are also same, and radius is also same. So with respect to 1, I will firstly put R dash. With respect to 2, I will put D. With respect to 3, I will put D. And then I will move to conductor number 2 with self R slash. Then with respect to 1, D. With respect to 2, D. And all these values I will write here. You understood that how I wrote the distances here, right?
Yes.
Okay, that's good. So we will again apply the same thing which we apply here, that we have to multiply all the distances divided by 1 divided by number of distances. So how many number of distances here? 1, 2, 3,
9.
4, 5, 6, 7, 8, 9, 9, right?
Yes.
Hello?
Can you hear me?
Yes, I can hear you. Now I can hear you. So can you hear me clearly?
Yes.
Okay, so here are number of distances are 9. So here I will put in power 1 divided by
9.
1 divided by 9. Here I substitute 1 divided by 4, and then I got after solving this I got 1 divided by 2. Here I will put 1 divided by 9, and look what I will get after solving this. So self GMD is equal to, I will multiply all the distances. So R multiplied by R multiplied by R. Firstly, I will multiply the R slash cube, R slash raise the power 3. So D multiplied by D, there are 6. So D raised the power 6 into 1 divided by number of distances. So how many distances we have? 9. So I put here 9. Here we had 4. So I put 4. So here I will just cancel out here. You will see that I will apply the power of 1 divided by 9 here. Then I will get, see how I can get.
Okay. What? Are you asking something?
Okay, let's solve this. Is it okay? R slash multiply by D square. Not okay, right?
You mean when you simplified it to 1 over 3?
Yes, we have to like we have 6 D's and we have 1 divided by 3. You can see.
Yes, I can understand it.
You can understand it, right? Okay, that's
I don't normally simplify it during questions, but I understand it. It's much easier if it's simplified.
yes, it's okay. So this is the distance we are talking about. That now in next slide I'm explaining. So this is actually the next slide is the last slide. I was preparing that. So now there are 4 conductors. For example, we have 4 conductors like this. So we have to know the distances like D, this distance. For example, sometimes we have conductor like this, okay? So we have equal distance between all these conductors, and we also should know about the distance of, this distance. Because before we solving this, we must know the distance between each conductor. Because here I know the distance from here, from this conductor to these 2 conductors. So there are 4 conductors. I should know the distance between from this conductor to 4th conductor. Sometimes conductor is here, so distances will be the different. in each case. If you know the basic idea, you can calculate GMD. Number of distances multiply, raise the power 1 divided by number of distances. Multiply all the distances, raise the power 1 divided by number of distances. Just remember that. So here, for example, is D. I should also know about, I must have to know about the distance of this distance and this distance. So the things become a bit complex here. So this D2 is the distance between these two conductors because it's not same. If you closely look this, the distances have this distance have changed because this is almost greater than this distance, if you will see. So we will call it, so we will, the same thing, we will calculate for conductor 1 self distance, then the conductor 1 to conductor 2 second distance, and then conductor 2 to 1 to 4 d2 this distance. But sometimes this distance is not given, so we have to use trigonometry, that like hypotenuse, you can say like h square is equal to b square plus p square. Hypotenuse square is equal to base square plus perpendicular square. Sometimes we divide this in triangle. So if I will know this distance and this distance, I can know this distance. Sometimes if I know. So this is this is mathematics. In next lecture we will solve problems, and then you will know about the how we calculate these distances and of each conductor. How to say, there's one thing I want to explain more, that okay, so now you know that how we calculate the self GMD, right?
Right.
So in when we'll solve the problem, we are not talking about the mutual GMD here. When we will solve the problem, we will directly calculate the mutual GMD. Okay. So now up to now, if you have any confusion, you can ask.
I have a confusion a little bit when I got the GMD and the GMR. I always confuse between them.
Oh, you always confuse between the mutual GMD and self GMD.
Yes.
Actually, it's actually the game of distances. So okay, in next lecture I will explain about the you can say that because the PPT is finished here. On tomorrow,
The mutual GMD is the GMR.
GMR. Yes, you can say that it's GMR. Yes, because in the first, you will see that in the first slide you saw here. The first slide, in case of single conductor, we call it GMR. Okay, but R is radius. So in case of two conductors, we cannot call it GMR. That's why we change its name. But by
So it's just the same. The mutual GMD is already the GMR.
yes, yes, it's the same. It's the same. But normally we call it GMD. In standard, we call it GMD.
My professor, they don't use my professor and the teacher assistant. They don't use the term mutual GMD. They just use it as GMR. That's why I was a little.
Okay, okay, okay. No problem. You can use GMR. No problem. But this is in case of standard. Yes, its distances have been increased. You just know the concept now, so you can use GMR. But normally we use it for a single conductor. Actually, it depends upon different books too. Some book use GMD, some book use GMR. So
Okay, so it's like the GMD in the if I'm getting the inductance of, let's say, a bundle three phase, so it's like 2 multiplied by 10 to the power of negative 7 ln GMD over the divided by the GMR, or is it like vice versa?
no, GMD over
Yeah,
divided by GMR. Yes. Actually,
GMD divided by the GMR.
yes, because self GMD is related with GMR because you know the same. It's the same phase. We consider it same conductor.
Oh, okay, so the self GMD is the GMR, not
Yes,
the
yes,
mutual.
yes.
Okay. I got
So here, I think let's see about your professor, how she uses, because I didn't see your professor notes. I just uh, how she called.
She doesn't usually explain, how to answer and stuff. It's the teacher assistant who does. I already sent you his
Oh,
notes, I guess.
okay, okay, okay. Yeah, this is a proof. I think she proved like no. What type of questions she gave in exam? Like problems, just problems.
Yes, she doesn't usually get any proofs. She doesn't ask about any proofs because we take exams online, so she thinks it's pointless to ask about proofs.
Okay, so she just talk about the problems, right?
Yes, the last exam I sent you, it was the midterm. It was a little complicated. We all got really bad marks.
Okay, one thing I want to explain between the wordings between, because I was sometimes a terminology is different, because you just like you said that GMR and I used self GMR, so GMT. So here is another unsymmetrical spacing. It's the same like I explained here. Okay, uh, in this slide, transposed line, we
The
call it.
transpose.
Yeah,
Okay.
these you can say that unequal spacing or unsymmetrical spacing is same thing. Okay,
Okay.
this is the same like she did here. That
Okay.
we are
Okay.
connected. But we will solve this problem too. Don't worry. I will solve all this problem in next lecture. So I have to actually go somewhere. If
Sure, no problem.
you want these, because I know I am leaving 20 minutes extra. If you can, if you are available tomorrow, I can teach you for half hour. No problem.
Can you repeat that, please?
What?
Can you repeat what you said, please?
I said that tomorrow, because I am leaving like 20 minutes before my promised
Okay.
time. So if tomorrow you are available, we can also study half an hour, about half an hour.
Uh, okay, I'll tell you if tomorrow I have any time because it may be a little at night. I don't know what's the timing in your country.
Actually, here in my country here it's 7:44. I think there is like 4:44, right?
7:44 p.m.
Here 7:44 p.m. 3 hours.
Yes, it's 4:44 here. Yeah, okay.
I'm three
I'll
hours.
let you know tomorrow because I have the lectures. Can I tell you on short notice or you need to know before it with a little bit?
No, no problem. Tomorrow is my off day. You can send me message. No problem. Anytime.
Okay, thanks a lot.
Okay.
Thank you.
Thank you.